Throughout this unit, we've been looking at a range of techniques that can be used to show that different expressions are equivalent. But a lot of those techniques we've justified using examples and observing patterns to argue that they mean expressions are going to be the same. In math, it's not enough to just recognize a pattern and assume the way it behaves is always true. But we want to use logic to justify what we're doing to make a convincing argument that what we have is actually true. Much of what we do in algebra is based on the following algebraic properties. The associative property of addition. So this says that if we have three values that are added, A, B, and C, we can either add A and B first or add B and C first, and we get the same result. If we add three numbers, we can do either addition first. The associative property of multiplication. This is similar, but this says if we have three values, A, B, and C, being multiplied, we can either multiply A and B first, or we can multiply B and C first, and we still get the same result. If we multiply three numbers, we can do either multiplication first. Now the rest of our properties we've actually already seen before, but let's go over them again so we're reminded how they work. The commutative property of addition. If we have A plus B, we can equivalently write it by switching their values as B plus A. We can change the order of terms in addition. The commutative property of multiplication. If we have A times B, we can equivalently write this as B times A. We can change the order of factors in multiplication. And finally, the distributive property. If we have A times the quantity B plus C, we can equivalently write it as AB plus AC. This property lets us distribute and factor. Now, most of the time, we don't need to think about these properties to work algebraically. Sometimes, however, we need to prove our work by justifying our reasoning using the properties. We can also use operations as reasons for our calculations. Let's look at an example of an expression being simplified. Now, this example goes into far more detail than we normally would to simplify an expression. In fact, you could actually simplify this expression in just 2 steps. But those steps include a whole lot of assumptions that we're making as we're working. What we're going to do here is break everything down into smaller steps to be absolutely clear we're using a logical algebraic property to get our result. So in the first step, you can see that for each set of parentheses, the number being multiplied in front is being rewritten so it's multiplying each term inside the parentheses. So what we're using here is the distributive property, because we've distributed both sets of parentheses. Next, we're going to rewrite the term 2 times the quantity 5x as the quantity 2 times 5 times x. This is changing which multiplication we're doing first. So this is an example of the associative property of multiplication. In the next step, we can actually perform some multiplication. So 3 times negative 4 is negative 12, and 2 times 5 is 10, and 2 times 7 is 14. Next, we're going to change the order of our terms because we want to have like terms together. What we're doing is switching the order of our middle 2 terms. This is an example of the commutative property of addition. Next, because our first 2 terms both have a common factor of x, we can take that out as a common factor. Now, factoring, if you remember, is the reverse process of distributing. What we're really using here is the distributive property. Next, I want to group my last 2 constant terms together. Really what I'm saying here is I want to do this addition before I do any other additions in this expression. This is an example of the associative property of addition, because that says we can do any addition that we want first. Finally, we can actually apply the addition of the constants that we have in each set of parentheses. So 3 plus 10 is 13, and negative 12 plus 14 is 2. So our final expression is 13x plus 2. And if you notice, now we have logically justified the reason we were able to do each step using one of our properties.